we are going to discuss components of vector. Consider vector A in the xy plane, and since there are two ends of the vector, the arrow end is called the head and the remaining end is called the tail of the vector. So I am writing, consider vector A in the xy plane. So we have this, and let the vector A make angle theta with the positive x-axis. Now let us draw a horizontal line parallel to x-axis from the tail of the vector. Then we find this angle is also theta. Now we drop or draw, okay? Drop or draw perpendicular from the two ends, that is tail and head of vector A on x and y axis. Okay, so let us drop perpendicular from the tail of vector A on positive x-axis. So this point represent the foot of tail, okay, on positive x-axis, and let us drop or draw perpendicular from the head of vector A on the positive x-axis. So this represent, okay, this point represent foot of head, okay, on positive x-axis. Now this line, okay, or this distance represent the projection of vector A on x-axis, that is positive x-axis. And if we move from this point, okay, that is from the foot of tail to the foot of head. So if we move along this direction, then this represent, okay, this represent the component of vector A along x-axis. So the projection of vector A on x-axis is the component of vector A along x-axis. So we need to note this, okay. Now in same way, let us drop perpendicular from the tail, okay, on the positive y-axis. So this point represent the foot of tail on positive y-axis, and let us drop perpendicular from the head, okay, on positive y-axis. So this point represent foot of head on positive y-axis. So this line, okay, or this length, it represent projection of vector A on y-axis, that is positive y-axis. And if we move from this point, okay, in this direction, that is in upward direction, then it represent the component of vector A along positive y-axis. So the projection of vector A on y-axis is the component of vector A along positive y-axis. So we have this. So I'm writing over here projection of vector A on x-axis, okay, is the component of vector A along x-axis. Clear? So AX is the component of vector A along x-axis. So this is to be noted, okay? And projection of A on y-axis is the component of vector A along y-axis. And what are AX and AY? So these are called, okay, these are called components of vector A along x and y axis. So this is to be noted, okay? Now we can see in this figure, okay, this is AX and this is AY, okay? We can see it. This is AY. So we have this. Now I'm taking this triangle, okay, over here. So this is AY and this is AX, okay? This is AX, this is AY, and this is vector A. So we have this. Clear? And this angle is theta. Now, in this triangle, if we find, since we know cos equals base by hypotenuse, okay? So base is AX by hypotenuse is A. So I'm writing in this way, okay? So we have this. Again, let us take or find sine theta from this triangle. So we know sine equals perpendicular by hypotenuse. So we have sine theta equals, and perpendicular is AY by hypotenuse is A. So I'm writing in this way, mod or modulus of vector A. So we have this. So we can write component of vector A along x-axis AX equals A cos theta. So we have this, okay? And component of vector A along y-axis is AY, and AY equals A sine theta. So we have this, okay? Now, let us call it equation 1, and this is equation 2. Now, what we do, squaring both sides of 1 and 2, okay, and then add, okay, and then adding, okay, we get this AX square plus AY square equals A square cos square theta plus A square sin square theta. So we can write in this way, okay, A square. So I'm writing in this way, cos square theta plus sin square theta, okay, A square is taken common. So this equals AX square plus AY square, and we know this is 1, okay? Therefore, we can write a square equals ax square plus ay square, or we can write a equals under root ax square plus ay square. So this expression gives the magnitude, okay? So this gives the magnitude of vector A in terms of its components. So this is to be noted, okay? Now let us find the direction, okay? Now in order to find the direction, okay? To find direction. So let's come to this triangle once again, okay? Or we can take this triangle. So we know tan theta, okay? And tan equals perpendicular by base. So we have perpendicular AY, okay? This is perpendicular, okay, to AX. So we see it from this diagram also. And base is AX. So we have this, clear? So we can find the direction, okay, from this expression. We can find direction from this expression, or we can simply write theta equals tan inverse AY by AX. So we have this, clear? So this is to be noted, okay? Now, I'm erasing this. Now, if theta is 0 degree, okay, then what happens? Let's see. We have this from this diagram, okay, or figure. We have plus x or positive x-axis along this direction, plus y. So if theta is 0, then we have this, okay. Vector A is parallel to the positive x-axis. Clear? In this case, okay, what we find, if we draw perpendicular from the tail, okay, and head, okay, then this line represent the projection, okay, it represent projection of vector A on x-axis. So this is called, or the projection of vector A on x-axis is called the component of vector A along x-axis, that is positive x-axis. Now, what we find in this case, okay, there is no component along y-axis, because you can see if you draw perpendicular from tail and head, okay, they are lying on the same point on the y-axis. So in this case, what we find, component AY is 0. There is no component, okay, of vector A along y-axis. So as we did, okay, magnitude of vector A equals under root ax square plus ay square. Okay, so we have derived it, and we know ay is 0. So we simply write a equals under root ax square. Therefore, ax equals, okay, magnitude of a. So we need to understand in this way. Okay, so we have this. So and there are few points to be noted. Okay, one, components of vector depends on the orientation, okay, of the coordinates axis. Clear? And next, the magnitude, okay, the magnitude of vector do not depend on the orientation of the axis. So this is to be noted. Okay,